All right, let's dive into one of the most exciting and, yeah, one of the most frustrating topics in AI right now, agents. We've all been promised these amazing autonomous helpers that are going to change everything about how we work. But the reality? It's often, well, a brittle mess. So why do they keep failing, and how can we actually build them better? Let's get into it.
You know, this quote from a random Reddit user absolutely nails the core of the problem. We're trying to build these super reliable, predictable systems on top of a technology that is, at its heart, a guessing machine. An LLM's job is to predict the next word, not to be a perfect source of truth. And that fundamental tension, that's what we're going to unpack today.
So here's our game plan. We'll kick things off with the huge gap between the hype and the reality. Then, we're going to walk through a real-world story of an AI agent that failed in some really fascinating ways. From there, we'll zoom out and look at a universal map of all the ways these things can break, check out some cutting-edge solutions, and then wrap up by tackling the biggest question of all.
Okay, let's set the stage. The promise of AI agents is just massive, right? We have this vision of these autonomous systems just flawlessly handling our most complicated tasks, acting like the perfect digital butlers.
But as anyone who's actually tried to build one of these things knows, the reality is a little bit different. The hype is incredible, for sure, but the engineering is a total minefield. These systems are so often incredibly brittle, and they break in ways you just could not see coming, turning that dream of efficiency into a complete debugging nightmare.
To really make this concrete, we're going to look at the story of an AI sales agent named Omega. It was built by a company called NetGuru, and thankfully they were super transparent about their struggles. Their failures teach us so much about what can go wrong. So, Omega was supposed to be a sales assistant that lived right inside Slack. It was actually a multi-agent system, so it had a few specialized bots for different tasks, a sales agent, a database agent, even a critic agent to double-check the work. The whole thing was hooked into their Google Drive and an internal knowledge base to give the team help in real time.
And right out of the gate, they hit problem number one, infrastructure. The goal was instant answers in Slack, naturally. But their serverless setup on AWS Lambda had this thing called cold starts, which caused delays of over 3 seconds. Well, Slack would get impatient, think the agent had failed, and send the request again. All of a sudden, the channel was just flooded with confusing duplicate messages from the AI. Whoops.
The next thing that broke was context. The agent needed to understand these long, messy Slack conversations. But LLMs have a pretty tight limit on how much text they can see at once, the token limit. Trying to cram a chaotic, multi-topic thread into that tiny window was basically impossible. The model just couldn't keep up, and its summaries became, as the developers put it, educated guessing. And finally, they hit a knowledge problem. They wanted Omega to act like a real strategic consultant, creating custom proposals for clients. But think about it. A human consultant does research. They go out and learn. Omega was trapped. It only had access to their internal documents. So without being able to browse the web, its answers were shallow, or worse, it would just confidently make stuff up.
Now here's the crucial thing. Omega's problems weren't unique. Not at all. They were just symptoms of these universal challenges that everyone faces when building agentic AI. In fact, Microsoft's AI Red team developed a whole framework for thinking about this, which they call a taxonomy of failure.
And what's really, really smart about this is how they categorize everything. They split the failures into 2 buckets. Novel failures, these are the brand new risks that have never existed before agentic systems, and existing failures. These are the classic problems we've dealt with for years, but now they're made way, way worse by an agent's ability to actually do things on its own.
Let's look at one of the scariest existing risks, memory poisoning. See, agents are designed to learn and remember things to get better over time. But what if an attacker could poison that memory? They could sneak in malicious instructions that the agent would then just recall and act on later, basically turning its own memory into a weapon against you.
And this example makes it chillingly clear how simple and devastating that could be. A bad actor tricks the agent into storing this one little instruction. From that moment on, every single time a real user asks the agent to send an email, it will also secretly send a copy of everything to the attacker. It's pretty scary stuff.
And the risk gets even crazier when you scale up to multi-agent systems, like this one Microsoft designed to investigate security alerts. Just look at this thing. You have all these specialized agents, a threat intel agent, a host analysis agent, all trying to coordinate.
This kind of complexity creates a whole new world of ways for things to go wrong.
Because in a system like that, every single handoff is a potential point of failure. It's like a game of telephone. Context gets lost as information gets passed from one agent to the next. If one agent fails, it can cause a cascade that brings down the entire team. Sometimes agents get confused about their jobs and step on each other's toes. And hey, let's not forget the tools themselves. The agent might use a tool perfectly, but what if the tool is just broken?
Okay, so things break. A lot. It sounds pretty bleak, but here's the good news. Researchers are coming up with some incredibly clever ways to make these agents more robust and more reliable. Let's look at some of the really promising ideas. One of the most influential ideas out there is the React framework. And it's so powerful because it's so simple. It basically forces the agent into a loop. First, it thinks about the problem step by step. Then, it takes an action with a tool. And finally, it observes the result of that action and uses that observation to figure out what to think next. It's a structured way for the AI to reason and learn from its environment, kind of like a person would.
Another huge breakthrough is happening in how agents use tools. For years, we've been forcing these LLMs to generate perfectly structured code, like JSON, to call a tool. And it turns out, they're not great at it. This rigid formatting can actually slash their accuracy by over 20%. A new approach, called Natural Language Tools, or NLT, makes this way simpler. Instead of writing code, the LLM just looks at a list of available tools and says yes or no to each one.
And just look at the results. It's stunning. Research shows that just switching from those structured tool calls to this simpler yes-no approach boosts accuracy from around 69% all the way up to nearly 88%. That is a massive leap in reliability, and all we did was let the language model speak in a way that's more natural to it.
And beyond these fancy frameworks, there are also just some practical, common-sense defenses we have to build. Organizations like OWASP recommend really smart measures you see here. Enforce the absolute minimum permissions an agent needs. Filter its inputs and outputs to clean them up. And this is a big one. For any high-risk action, make sure there's a human in the loop who has to give the final okay. Don't let the agent go completely rogue.
Which, of course, brings us right back to where we started. We have better frameworks, we have better ways to call tools, we have better security, but we are still left with that fundamental, almost philosophical challenge at the very core of this technology. Can we really ever build foolproof, 100% reliable systems on a foundation that is literally designed to guess? We are layering all this deterministic, predictable logic on top of an engine that is fundamentally creative and stochastic. Is that a stable foundation for the future we're all trying to build?
And you know, maybe that's the real takeaway here. Perhaps the goal isn't to build an agent that never, ever fails. Perhaps the real art, the true engineering challenge of our time, is to build agents that understand their own limits and have mastered the art of failing gracefully. Thanks for watching.